video, we're going to be describing the rational zero test. How can we find some possible rational zeros of some polynomials? We'll figure out that in some cases it's helpful, in other cases it's not as helpful. And then mostly though, we're going to be just solving polynomials using a variety of different methods. So first, let's talk about what it means to be rational. Because if we understand what it means to be rational, then we'll understand what a rational zero is. A rational number could just be a whole number, but it could be positive or negative, which means that it could be an integer. So integers are just positive and negative whole numbers. But it could also be a fraction or a decimal value. But in order to be rational, that fraction needs to turn into a decimal that either repeats or stops, and that would be a rational number. So the rational zero test is only giving us possible zeros that are either integers or fractions or decimals that repeat or stop. So it's not going to give us irrational zeros, and it's not going to tell us anything about imaginary zeros either. So it's kind of limited in that way. The rational zero test came from a time when we didn't have calculators and people had to do this the long way. However, now we have graphing calculators, and we can look at those instead, but it's also nice to just have as many tools as possible when we're trying to narrow down what our zeros are for polynomial functions. So let's try out one to begin with, this x cubed plus x plus 4. To state the possible rational zeros, we're going to create a quotient here where we're going to take factors of our constant term. So the constant is always the number by itself, usually at the end of the function. And then we're going to divide that by any possible factors of our leading coefficient. The leading coefficient would be the number in front of your leading term. So in this case, it's 1. So let's take factors of 4, like 4, 2, and 1. But it is true that we could have negative 4 and negative 1 as factors of 4. So our list of factors is always going to include positive or negative values. So positive and negative 4, positive and negative 2, and positive and negative 1 are factors of 4. Now on the bottom, we're going to divide by factors of 1, that leading coefficient. So the only factors of 1 are positive and negative 1. If I divide by 1, well then nothing's going to change on top. So if that coefficient, that leading coefficient is 1, then actually your possible rational zeros are just the factors of your constant term. So we have 6 possible rational zeros: positive 4 and negative 4, positive 2 and negative 2, and positive 1 and negative 1. We can use our brain just a little bit before we use our calculator. If I have a bunch of terms being added and I plug a positive value in, well, would that ever be possible that my output would be 0, making it an x-intercept? I don't think so. So we can eliminate those positive possible rational zeros. So let's just check the negative ones. And we can check by just plugging values into the function and seeing if we get 0 out. If I plug in negative 1 cubed is still negative 1. Minus 1, that's negative 2, plus 4 is 2, so that's not going to equal 0. If I plug in negative 2 cubed is negative 8, minus 2 is negative 10, plus 4 is negative 6, so that's not helping. We seem to be getting farther away. If I plug in negative 4, I'm just going to be an even worse result. I'm still not going to equal 0. So out of the possible rational zeros, none of them are actual zeros. So let's take a look at your graphing calculator. Take a look at the graph of that, and you'll see that there is only one 0, and we should be getting 3 zeros out of it. So on the graph, only seeing 1 0 would lead us to believe that we have 2 imaginary zeros as well. That 1 0 that we see on the graph is actually not a rational number. You can use your calculator to evaluate it. It actually turns out to be an irrational 0. So it's an irrational number. It is a 0. It's just not a rational one. So our rational zero test didn't help us determine anything. So there's a case where the rational zero test actually doesn't help at all. Let's take a look at one that it actually does help us a little bit on if we choose to use it. Let's find the possible rational zeros again. So we're doing this first step. We'll just get an idea of what zeros might happen that are rational. If I take factors of 8, like positive and negative 8, positive and negative 4, positive and negative 2, and positive and negative 1, and I divide that by factors of my leading coefficient, which is just 1 again, well then the result is just the factors of that constant term. So this time we have 8 possible rational zeros. We can take a look at our graph, and we can narrow that down a little bit. So here is the benefit to the rational zero test. It tells you what are some of the possibilities, and you can use some other tools to help you narrow it down. So looking at the graph, we probably see that -1 seems to cross the x-axis at that point. And maybe you can tell that it also maybe passes at 4 and at 2. Notice that those are all possible rational zeros that we determined. One thing you can do is look at your data table, and you can verify at either of these 3 points that that's an actual 0. So if your output is 0 at any of those points, then you've verified. You could also plug values into your function if you don't believe your data table. And obviously you'd want to probably plug in the easiest numbers first, just to see if any of those work without having to test any of the other ones. So plugging in +1 or plugging in -1 would be a good first guess. As it turns out, if we plug in -1, we get a result of 0, so -1 is a definite root, and we can verify that on the graph and on the data table. So we're going to be able to use that and divide to factor our polynomial. So using -1 and synthetic division, let's divide this polynomial by -1. The result we get has a 0 remainder, which again verifies that that is a root. And the results allow us to rewrite a factor pair 1 degree less than what we started, so we're going to write a quadratic using these coefficients. Don't forget that first one that we decided, so the factored form of -1 would be x plus 1. And then the resulting quadratic using those coefficients, x squared minus 6x and plus 8. Now that we have a quadratic, we can use a quadratic factoring pattern. We just have to find factors of 8 that add up to -6. Hopefully you know that's -4 and -2. So now we have our fully factored form of that polynomial, and the zeros are the opposites of what your factors are. So -1, +4, and 2, the exact same values we thought we saw on the graph, and those are all rational zeros that we found using our rational zero test. So lots of ways that we can verify everything that we're doing. Let's do another one, a little bit trickier now. Again, we can take that rational zero test and come up with some possible rational zeros that we can use to divide and factor. So we want factors of our constant 3 divided by factors of our leading coefficient of 2. 3 has 2 factors, well actually 4 factors, positive and -3 and positive and -1. 2 has 4 factors, positive and -2 and positive and -1. Now because we have more things happening on the bottom, when we divide, it's going to be a little bit trickier. I like to divide one of my top numbers by all of the bottoms and then move on to the other following top numbers in the numerator there. That way I just stay organized. It's not necessarily in numerical order, but that's a way that I can stay organized. So positive and -3 divided by positive and -2 is positive and -3 halves. And then if I divide 3 by 1, I get positive and -3. Done with 3, I'm going to move on to 1 and divide it by all the bottoms. So 1 divided by 2 is positive and -1 half, and 1 divided by 1 here is positive and -1. So we got 8 different possible rational zeros. We could plug any of these ones into the function, see if we get a result of 0, but that might take a little while. I would rather look at my graph. So if we graph this polynomial, we should be able to see some zeros that may be listed here. One of those we may find is -3. So on the graph it looks like it crosses at -3, and that was one of my possible rational zeros. So I'm going to use that to divide and see if I get a result of 0. So using synthetic division, I see that my remainder is 0, once again verifying that -3 is in fact a root of this function. So its factored form would be x plus 3. My result down here is going to be a function 1 degree less than the cube, so I'm going to start with my quadratic, 2x squared minus 3x plus 1. Now all we have to do is factor that quadratic. You can use the quadratic formula if you want at this point, if you don't know how to factor that type of quadratic. I think it's easy enough that we could just guess and check, knowing that 2x squared is going to be the factors 2x and x, and now all we have to do is figure out what to put in these spots so that when we distribute, we add up to -3 and multiply to +1. Well, if we're multiplying to +1 for these last spots here, we know it could be 1 and 1, or -1 and -1, so you really only have two choices to put there. Putting +1 in that spot doesn't work out, so we put -1 in that spot. Quickly FOIL or distribute to check. 2x squared, -2x minus x is -3x, and -1 times -1 is +1. Now we have this cubic factored into these three factors with zeros of -3, 1/2, and 1. And then lastly, again, we look at our graph and verify that that's what we got, or we can look at our data table. All right, one more. This is kind of a monster. We got this big quartic or fourth degree polynomial. Notice that all of the terms have an x and we don't have a constant term right now. So in order to use the rational zero test, first you always want to factor and get a constant. So because I can factor x out of all of these and the result leaves me with a constant, that's always going to be my first step if I can. In factoring out an x, we can see that that's going to be our first x-intercept, x equals 0. So we got one real. We're looking for 3 more though. We're going to look for a total of 4. So now we have this cubic that we got to deal with, and we can actually use the rational zero test and see what happens. We got factors of 12, where there is an awful lot of factors of 12. 12, 6, 4, 3, 2, and 1, all positive and negative. And we have a few factors of 10. We got 10, 5, 2, and 1, again, both positive and negative. And if I do my division and I list them out, there's actually quite a few of them, way too many to deal with. If I didn't have a calculator, well, I guess I'd be stuck and I'd have to try and use those. But because we have technology nowadays, we can look at the graph and determine which of these are not possible and which of them are possibly possible, I guess. So looking at our graph, we can see that we're crossing at 2. 4 divided by 2 would have given me that possible rational zero. So according to the test, that's real. According to my graph, that works out. I can also look at my data table and verify once more that if I plug a 2 in, I get a 0 out. So I know I can use 2 to divide and factor my polynomial. I'm going to use the factors from this polynomial because I've already factored from there to get there. As you can see, though, they're the same coefficients. The only question would be, what do I do with the result? So if I have this result, am I doing 1 degree less than the fourth or 1 degree less than the cube? So we're really doing 1 degree less than the cube because we've already gotten to that cubic stage. So the results are going to be a quadratic. Now let's list what we got so far in our factors. We have x from that original factor. Now we knew that 2 was a root, so x minus 2 is going to give me the factored form of that. So I got 2 real zeros happening. I need 2 more. Are they going to be real? Are they going to be rational or irrational? Or are they just going to be imaginary? So one thing we can do is we can try and factor this quadratic. Turns out not to be factorable. There are no factors of -60 that add up to 5. So maybe they're irrational, or maybe they're imaginary. One way to check is to use what's called the discriminant. It's the b squared minus 4ac part of a quadratic equation. The result will tell you whether you have real solutions or imaginary. So let's plug the b value of 5 into that spot, a value of 10 into that spot, and -6 into the c value. We actually don't need to know what the number is. We just have to realize, is it going to be a positive result, a negative result, or a result of 0? And I know that if I'm going to be multiplying a negative times a negative, I'm going to get a positive. And adding a bunch of positives together is just going to give me a positive number. So I know that because I have a positive result from my discriminant, I'm going to have two real roots. And so now that I know that they're real, and I know that they're not rational, well then they must be two irrational roots. So in order to find them, we got to use that skeleton key. We got to use our quadratic formula. That's going to help us solve any quadratic. By plugging our a, b, and c values into the quadratic equation, we can simplify to this form. This would be the simplified form of my two zeros. However, this doesn't help me check it on a graph. So in order to check it on a graph, we want to take it all the way down to its decimal values, and then we can compare those values on our graph and make sure we're close. So I got two values here. I got to take this into two equations. It's -5 plus the square root of 265, all divided by 20. That's going to give me this positive result of 0.564-ish. I'm rounding to the third decimal place there. Then my other value is going to come from -5 minus the square root of 265 divided by 20. And that result is going to give me this -0, again rounded to the thousandth. If I look at my graph and I use my calculate feature to calculate the zeros for each of those two spots, then my calculator can approximate it pretty close, and I can verify that I was correct there. So I got my two irrational real zeros and my two real rational zeros, giving me my four total zeros. All right, so there is a little explanation about the rational zero test. Again, it's a tiny tool. It's kind of useful, but it is somewhat outdated and limited at times. But we always want to use any tool available to us. So that's one possible tool that we can use in addition to looking at our graph, using our data table, and dividing and factoring to solve our polynomials.